Starting. All attendees are in listen-only mode.
Good morning, everybody, and welcome to today's webinar. My name is Cheryl Jennison DeProza, and today we're going to be talking about networking basics for audio professionals. I am joined today, as always, by Gino Sigismondi, Manager of System Support. And today we are joined by Sam Drazen, who is a user experience designer here at Shure. They're going to talk us all through Networking 101. But before we get into the webinar, just a few items of housekeeping. First of all, this webinar, as they always are, is being recorded, and it will be archived hopefully sometime early next week. So if there's something you need to go back and revisit, or you want to direct a colleague to this, or if you want to go through any of our old archives, you can always find them at shure.com/training. That is where our webinar archive lives. So feel free to peruse all of the great past webinars we've had there. Second of all, as we go through today, if you do have questions, you will notice in your little module in the right-hand corner of your screen, there is a little question box. Please feel free to ask any questions as we go through. We will get to as many of those at the end of the webinar. If you can't see that pane, there might be a little toolbar with an orange arrow. Just click on the orange arrow and that will maximize that little pane, and you can see that question box then. And then just one last item, just wanted to let everybody know that we are going to be at InfoComm June 18th through the 20th in Las Vegas. So if you are at InfoComm, please feel free to stop by and visit us. We're going to be at booth C10108. And we're going to be doing some great little educational seminars and sessions at the booth. So please feel free to stop by, check out some of the educational seminars. And if you have any questions that we can't answer here today, please feel free to stop by that booth and ask us there. So without further ado, I am going to pass it over to Gino and Sam. Take it away, guys.
All right. Thanks, Cheryl.
Thanks, Cheryl.
Thank you, Sam, for joining me here today.
Oh, thanks for having me.
Appreciate having your assistance on this very important topic, networking basics for audio professionals. And that title hopefully sums up the slant that we are going to put on this topic today, because it's a big topic. And you could, well, I mean, I think Cisco certification courses, actually, I can't remember the number of hours it takes, but it's a significant, it's in the months of preparation, I believe, to be able to get to that. So if you signed up for this course expecting this webinar, expecting that you would come out of this able to be a Cisco network IT manager, I hate to break it to you, but we're not going to get quite that in detail today. What we really wanted to do was take kind of a higher level look at really what are the important things regarding networking and IP addressing and things like that that you would need to know when working with audio products that rely on that technology. Again, the little blurb that kind of described this webinar that you probably saw when you signed up for it featured a joke that I admit stealing from a customer, but I thought it was a worthwhile one, which is, you want a career in audio, how's your back? And now it's, you want a career in audio, how's your networking chops? And that's really kind of true these days. The whole reason that my department, which is called the System Support Department, exists at Shure, which is really a offshoot of our applications engineering department, was because so many of our products now rely on networking, not just like the the original UHFR, which came out in like 2005 and was the first Shure product with an Ethernet jack on it. It was like, hey, look, you can network it. You don't have to, but some cool stuff happens when you do. A lot of the stuff we have now, you have to network it together. It does not work if you do not hook things up on a network. So that's not true. I mean, that's true of things beyond just Shure products. So in the world of audio, you're finding more and more that you do have to rely on networking. So with that said, we're going to try and again take a high level look at some of the important topics that will help you get by in the world of IT. We'll start with just a basic definition, though. The word network gets thrown around a lot, but I don't think anyone that really anymore takes a step back to think about what does that word even mean, or where does it come from? And the real definition of a network, which is also stolen from one of our engineers here at Shure, he describes it as two or more like elements working together to solve a problem. And that really is true. I mean, and that description has nothing to do with computers specifically. It's just anytime you have that, those elements trying to do something, that's a network. Obviously, in today's world, that usually does mean some sort of computer digital based products. But again, if they're not solving a problem, then, well, there's really no point to even having the network. So we're trying to connect these things together to make some audio task easier in some way, and that's what we're doing here. Second thing is that a successful network also requires specificity, and that really gets into what we're going to talk about specifically with addressing. So, so that again, that's something that is important here. Is that when we're talking about IT networking, we're really talking about giving things specific addresses, and if you're not specific, then the network basically it doesn't work, and that's really most of the problems that it comes down to here when we help people troubleshoot our networkable products. 9 times out of 10 it comes down to something not being as specific as it should be, and we'll get more into that when we talk about the addressing here. So here's what we're going to cover today. We'll get into the physical hardware and the cabling and that as a place to start, and then dive right into the IP addressing, which is really the heart of the matter here, and then talk a little bit about getting your computer involved in that network, because most of the times when you're putting things on a network, there's some sort of computer control software or something that needs to be part of this too. And finally, we'll take a little bit of a look at networked audio, which is of course audio running on essentially on a computer network. So that's what we're going to talk about. We'll start with hardware and standards. And as I mentioned earlier, cables, connectors, switches, and routers, the concept of bandwidth, and a little bit about cable topology. Sam?
Yeah, let's just cover a little bit about. You've probably heard some of these cable types or names have been thrown around. Cat 5, Cat 5e, Cat 6. These are types of cables, and in essence, a twisted pair cable for data transmission is how you would define some of these cables. As the standards have progressed, cables have gotten more able in terms of being able to pass more data through with higher bandwidth, or being able to impose more stringent requirements to reduce crosstalk or noise or interference. And I guess you don't need to know a ton about these cables other than the fact that some of the devices you might be networking may have requirements that they need certain types of cables. So I think a takeaway from this slide is to know that different types of cables exist, and there may be a requirement when you're networking some devices together that you have to get the right type of cable.
In general, you're not going to encounter Cat 5 too much anymore, and most of the products that we're putting out and anything it's going to connect to is typically going to specify Cat 5e or Cat 6, which again is not. It's probably what you're going to encounter anyway, but that's primarily the two types that we're looking at here.
Some of the connectors you'd see on the end of these cables are called RJ45 connectors. We've all seen a connector like this before. It's a standard Ethernet connection. It's comprised of 8 pins or 8 wires going out. And this is an example of a plastic housing in a cable. An alternative sort of connection is a shielded RJ45, where you see the connectors actually metal on the sides. And this is often required for networked audio applications, just to reduce, interference or strengthen a signal transmission.
Just like you would have shielded connectors and shielded cable in an audio application to keep interference from messing with the integrity of the desired signal. The same thing happens here, and that really becomes critical when you talk about networked audio, because the way interference impacts stuff traveling down an Ethernet cable is things like packet loss, which if it's data is not a big deal because error correction just puts back whatever was lost. But in real-time audio, it becomes a little bit more critical to have as little loss of data as possible, because it's actually happening in real time, unlike when you're opening up a picture of your kid in an email or something like that. So specifically with the networked audio, the shielded RJ45 becomes kind of a critical thing.
Switches and routers. This is a topic I'm sure most of us have heard terms switches and routers before. At the highest level, a switch or a router are both examples of devices that enable you to network multiple network devices together. You connect a lot of devices through a switch or a router. And a point to make is that switches and routers are both sold as consumer and professional products. You can spend $20 on a cheap router and $2,500 on a really nice router. And all that to say, you don't always necessarily want to cheap out and buy the cheapest possible thing, but which piece of gear you use and the features that it has should be dictated by the application. A lot of these routers and switches have features like DHCP capabilities, which we'll get into in a little bit, PoE or Power over Ethernet. So I think we're going to discuss the differences between switch and routers in the next slide. But
yeah. And just to kind of hammer home the point about the difference between consumer and professional products, you got to look at what you're asking this device to do, right? Because we do encounter a lot of situations where someone is spending, $20,000 on a Shure MXW wireless system for a conference room, and then they go to Best Buy and throw a $30 Ethernet switch in there, and that switch is kind of the hub of the connectivity of these devices. So do you really want your $20,000 wireless system depending on a $30 switch to make sure everything is going to work? So whilst in some instances the consumer switch, grade switch may work for you, again, think about the scale of what you're trying to do here and try to choose an appropriate device.
So I wanted to demonstrate, or at least display, a really high-level comparison of what a switch and a router could do. And somebody in the last webinar corrected us here, and I'll speak to where there might be a little bit of an error here. But if you look at the left, this indicates sort of the function of a switch. A switch is a thing that multiple networked devices connect to. And a router, in comparison, routers can often enable you to connect multiple devices together, but the key differentiator between a router and a switch is that a router has the capability to connect you to another network. The most common instance of this we're probably used to seeing is the router in our homes, which can connect the devices or the network devices like the computers in our house to the World Wide Web or to the internet. A router can also connect you to another router that's connected to another network of devices. But the key difference between these two is that a router touches another network and a switch maintains just a small local network of devices.
Okay. And right, and the point that was made in the last webinar is that technically, as illustrated here, the router would actually be a router with a switch built into it, because a pure router would really just be used to connect two different networks together. But for all practical purposes, again, the thing that you go to Best Buy and buy that's called a router typically has a switch built into it, at least at the consumer level there.
Mm-hmm.
So, but both devices exist, and routers with switches built in can of course be used for the types of applications we have here. The thing that's not shown on this slide that you sometimes people hear one or both of these devices referred to as a Ethernet hub, and hubs are almost non-existent anymore. But a hub is really kind of a dumb device that doesn't allow you to do any sort of intelligent routing of the signal at all, like can happen with an Ethernet switch, and they're not very useful for the kinds of traffic that we're dealing with on networks today. So, but just so that you keep things straight, when you're talking to the IT department, you really don't want to walk in and ask them, so what kind of hub do you guys got? Because then the IT guy think, what are you talking about? We don't use hubs here, right? So you really want to make sure, just for terminology's sake, a hub is not something we're even really dealing with anymore.
And we'll illustrate in a few slides here what Gino meant by some sort of intelligence in terms of routing messages from a destination to, or an origin to a destination, which will maybe make that a little bit clearer. Bandwidth. I mean, we're all familiar with this. Anytime you're passing data over a cable, there's a certain amount of data that can travel at a certain amount of time, and Ethernet cables are not, exempt from that sort of restriction. So all networked devices are rated for certain speeds. If you've got, a wireless receiver that's networked or any sort of device, it can send data at a certain rate, and it's likely if it's going to be receiving data, it can receive data, either control data or audio as data at a certain rate as well. And again, the thing to be aware of here is, based on the piece of gear that you're using, be aware of the bandwidth speeds, the rate at which it can send and receive data. Common data rates for Ethernet include 100 megabit, gigabit. You've seen these before. I'm sure as time goes on, we'll be sending data faster and further, but this is really just a thing to be aware of when you're either buying gear or buying cables, making sure that everything lines up in terms of functional ability.
This is definitely one of those check with the manufacturer things, right? Because, for example, Shure MXW, again, to keep using that as an example, really requires a gigabit network. And so that's something that you want to communicate to the IT department. If you're putting an MXW system in a corporate environment and it's going to be living on the corporate network, it needs to have gigabit connectivity. That's gigabit switches or routers. If you've got PoE injectors there too, like power over Ethernet injectors, those need to be gigabit. Everything needs to be gigabit. So it's, that's kind of why we point out the differences here, is that these are specifications of the hardware, and everything needs to match up to what the manufacturer recommends for the particular type of device.
So we wanted to talk a little bit about topology. And for those who aren't familiar with the term, topology just means the arrangement or orientation that you hook gear up together. So this is an example of what one would call a daisy chain topology. you're looking at some ULXD 4Q receivers. These are just some of Shure's wireless microphone receivers, on the back of which are 2 Ethernet jacks apiece. And so this enables us to hook up devices in a daisy chain topology where one of the cables from one device goes into the other cable of the other device, and you can sort of link one device to each other without any external switch. So this topology is beneficial because you have to use less cables and you might have a neater bundle of Ethernet cables in the back of the device. But the downfall is, bad stuff happens. And let's say you were to lose a connection between one half of your gear and the other. This might look bad. It might not look so bad because you have now just 2 independent networks of gear that might be able to be managed. But bring in a laptop to the mix that you might be controlling all of this gear from, and that control interface touches only one device of this topology. Now you just lost connectivity to half of your devices. So that's why we tend to advocate more for what's called a star topology, where every network device in a network that you're controlling has a home run connection to your central switch or router. And the benefit of this sort of topology is when you lose a connection or for some reason a cable goes bad or a device goes down, uh, any sort of control application running on a computer still has access to all the other devices, and one bad device or cable doesn't spoil the bunch.
And so we get asked often too. It's like, well, you don't recommend doing it, then why do you put 2 ports on there? And it's like, well, a couple of reasons. In this particular case of ULXD, it's because the Dante card, there's ways you can configure Dante that actually require having 2 ports. But in its default configuration, it is just a 2-port switch. And if you're just doing a single hop, sure, connect one receiver to the next one and you're done, and you throw your computer on there and it's easy to do. And a couple of switch hops like that is probably okay. But so for convenience sake, it's there. But the recommended way to do it, and really this goes whether it's for the Ethernet or whether it's for the antenna connections, because there's cascade ports on that too. It's a cascading. Daisy chaining is a convenient way of doing things, but the star topology is always a more reliable and robust way of connecting things.
You just mitigate the risk of cables breaking, which is certainly something that everyone's had experience with,
Exactly.
And other certain failures.
When we first shipped the UHFR receivers, again, our first Ethernet enabled device, it had a single Ethernet connection on the back. And I wish I had $1 for every time someone called and said, why didn't you guys put 2 on there so I could daisy chain these things? So we've had this conversation many times and explained to people why we didn't put 2 on there. Not just real estate reasons, but because you really don't, for a large system, you don't want to be daisy chaining one to the next to the next. An external switch is definitely recommended.
So moving on to IP addressing, this is probably the meat of this webinar here. There's a lot of stuff to talk about. IP addressing refers to getting your device's unique IP addresses, and we'll dig more into that in a second, but I think there's some high-level definitions that we should cover first. The parameters the things that we've shown here under definitions: MAC address, IP address, subnet mask. They're all fields or values that a networked device could have associated with it, or does have associated with it. And they each mean something different. So let's start with a MAC address. A MAC address is a unique identifier of a networked device. You could think of this as the one name that a network device could have that could never mean anything else to anybody. It's completely unique to that device. The way it's represented is typically with a 12-digit hexadecimal series of characters. That hexadecimal characters 0 through 9 and A through F. And the orientated, like the manner in which these characters are displayed, corresponds with an IEEE standard, the 802 standard, and it is laid out in the following. You see the giant set of digits at the bottom of the screen. The first 3 octets, or groups of values, correspond to the specific manufacturer. So Shure will have its own 3 octets of a MAC address that every one of Shure's devices has. And the last 3 octets are freely assignable by the manufacturer. So back to Shure, our example, it's our business to make sure that every MAC address.
Can see.
Oh yeah,
there it is. That's from a Shure device. In case you were wondering what the Shure MAC address was. Sorry.
Oh no, it's okay. it's good to put it in context. And then it would be our business to make sure that those last 3 octets are unique for every device that we ship. So this is, you can think of this as like the be-all end-all unique identifier of a particular device that lives on a network.
So no 2 devices, Ethernet enabled devices in the world will have the same MAC address. They are all independently unique, and as you can see, the standard provides for approximately 280 trillion MAC addresses.
Yeah, for those who are curious, actually, this standard is an old one. They've trying to deploy a new standard out that extends this even more and gives more options, more than 280 trillion possible MAC addresses. But suffice it to say, it's unique for every device. Bringing us to IP address. So I like to flesh out an analogy here of sort of like a house. An IP address is the address of a networked device. So you can think of this in a house analogy. It's the address. It's how the mailman knows to put mail in your mailbox. It might be written on your mailbox somewhere. It doesn't really refer to the house as much. The house is kind of like your MAC address. It's the unique physical entity that's different than everything else. But the IP address tells other people how to get to you. So an IP address, as I said, is a device's address on a given network. It's comprised of 4 numeric values, also called octets. But each one of these octets is a numeric value only that is between 0 and 255. Now, on a given network, and there can be many, so like talking about one scope of a network, if you've got a few network devices that you're working with, each device must have a unique IP address within that given network. And I think talking about scope in a little bit will help us clarify that.
That's that specificity thing again.
Yeah,
right?
exactly.
Unique per device.
They don't just happen. You got to make sure you build a network up properly. This is an example of a very common IP address you might have all seen: 192.168.001.042. Each one of those sets of three digits is considered an octet. So this is an example, kind of going back to what Gino was saying earlier, that it sort of touches on how a switch can intelligently manage communication from more than one device. But in this example, we've got 4 devices. They all have very similar IP addresses, but the digit that's bolded sort of indicates the fact that each network device has a unique IP address, ultimately unique, even though it might be very similar. And when these devices communicate with one another, let's say 45 wanted to send 44 a message. That message would go to the switch, and the switch knows the other devices and their IP addresses that it's connected to. And a message can literally be sent from my house to Gino's house. You could think of it that way. And the mailman is represented by the yellow lines here, or that network communication through a switch.
And the fact that all those numbers are so similar, right, is important here. And that's it's going to tie into the next topic of the subnet RASC, right, is that every IP address on a device needs to be unique, but it doesn't mean it can be just some random set of values of whatever it happens to be. It needs to somehow be defined somehow so that these devices are aware that they're on the same network.
Mhm.
Because just being on the same network doesn't mean these devices are all plugged into the same switch. You can have a bunch of devices plugged into the same switch, but if the IP address is not assigned and defined properly, then you still don't have a network. And that's where the subnet mask comes into play.
Yeah, so a subnet mask, it subdivides a network to a range of IP addresses. That's the definition. But functionally, in like human speak, what you would say is it defines the neighborhood that all the network devices exist in. You can think of the subnet mask sort of setting the scope for where a mailman could deliver letters. That's sort of the analogy back to the house again. When a subnet mask is defined, it sort of builds a little community where network devices can communicate with one another, and it sets up the rules for which IP addresses are considered in that subnet and out of that subnet. And that's absolutely vital when you're getting network devices to communicate with one another. Talking about its composition, it's comprised of 4 numeric values as well. Each octet, though, is, instead of ranging between any one of these 3 values from 0 to 255, typically you'll see subnet masks each octet either being 255 or 0. And there's a very explicit meaning that both of those values have. I think does the next slide get into this? Let's see. Okay. So what happens is subnet masks, they open I like to call a value of 0 as open. And the reason I like to call it that is when an octet in a subnet mask is set to 0, the associating IP address for that device, the associating octet can be, that's the value that can vary as well. So I guess to step back a second, every device has a subnet mask and an IP address. And if a device has a subnet mask of this top subnet 255.255.255.0, what that subnet mask defines is the first 3 octets, those that of the IP address, those that correspond with 255, must all align. So all of the IP addresses on this device, on this network rather, must be the same, and only the IP address octets of this last octet here can differ. So we're going to see that in a second, how that pans out. So here's an example. We've got a subnet mask where the first 3 octets are 255 and the last octet is 0. And down below, we show IP addresses that could potentially be in that range. The first 3 are valid. And the reason that they're valid is that all of the IP addresses, their first 3 octets are the same. And the last octet, the one corresponding to where 0 is represented in the subnet mask, are different. And they have to be different so that they can uniquely identify one another. This last IP address, however, would fall outside of the subnet. It would not be a valid network device because the third octet, it should be similar with all the other network devices. However, it's not. It's set to 2 instead of 1. And another example of how subnet mask can limit the size and the scope of a network is, in this example, the last 2 octets are open or set to 0 in the subnet mask instead of just the 1. So instead of having roughly 250 available IP addresses where just the last octet of the IP address could vary, now we've got roughly 250 squared IP addresses where the last 2 octets of the IP address can vary. So you'll see the example down below shows that the first 3 IP addresses, they're good. They're even Steven because the first 2 octets match all of the other devices. But that last IP address differs in one of the octets that's supposed to be consistent. So that's a lot of numbers, but hopefully that what you should take away and understand, if anything, is the relationship between a subnet mask and then the IP addresses that dictate what's valid for that subnet of devices.
And just to drive the point home, when we're going to talk in a minute here about how devices get an IP address, but we've already said that every device needs to have a unique IP address on a given network, and the subnet mask needs to be the same on all devices. So that's always a quick thing to look at when things aren't talking to one another and you're trying to troubleshoot IP addresses, is don't just check the IP addresses, but check the subnet mask too, and make sure that you've got a matched subnet mask on every device. And in the examples we've looked at here, we've seen basically 2. We've seen 255, 255, 255.0 or 255, 255.0.0. And the reason for that is because in probably 99% of applications you're going to run into, again, unless you're integrating on some large corporate network in a large facility that's very, highly managed, those are the 2 subnet mask values you're going to encounter. Yeah, that's what you're going to see.
And there's something, an earlier slide sort of called out, I just want to make mention real quick. You'll notice that the zeros come in from the right to the left, or they occupy the least significant octet first and then move more and more significant. And that corresponds exactly with what Gina just said. The more octets you open or set to 0, the bigger the scope of the network is. And it's generally prudent to not have a bigger network occupying more IP addresses than you need. You want to sort of keep things contained. You'll both mitigate risk on your end from other network devices interfering with you, and also just limit the sandbox that you're networking in.
So with the subnet mask of 255, 255, 255.0, with that one, the possible range of IP addresses you can use is only slightly more than 250 IP addresses. It's actually not 256. It's a little bit less than that. But that's, for most networks and smaller applications, that's plenty of IP addresses. But if you needed more than that, if you've got thousands of devices on your network, then you need to essentially release another octet with your subnet mask, and that, because now you've got the last 2 octets of the IP address can vary, and that gives you a much larger range of variables, and that can keep going.
Fortunately, this might not concern you at all if you're not the one managing IP addresses, but this is a little glimpse into what some of the low-level decisions that an ID department might make, or somebody who's the network administrator.
Before we move into this, I just want to mention something that was on an earlier slide. We don't really need to go back to it, but it was the concept of ports. And we just wanted to introduce that topic here because we kind of come back to it a little bit later at the end. But the ports, to go back to Sam's house analogy, then ports refer to like what would be the doors and windows on your house. And there's certain communications that have to happen on a network, and the ports for those communications need to be opened up. And normally this isn't something you need to worry about. But again, when you're integrating with a larger corporate network, they may they may manage the network so tightly that certain ports that you need, for example, to run the GUI on one of our devices to control it, those ports might be shut down, which is the equivalent to the door being locked and nobody home when the UPS driver knocks on your door. Then you don't get your delivery, right? Because that port is closed. And so you have ports on a network as well. And we'll revisit that in a little bit. But in case you saw that word on an earlier slide, that's why it was there. And we'll talk more about that in a minute. But let's talk about now, how do you get an IP address?
Yeah, so this is really where the rubber hits the road here. I think oftentimes in your networking devices, you'll probably be in one of a few scenarios, but something to add to your checklist to know about any network, whenever you're networking devices, is how the devices are supposed to be getting their IP addresses. And there are really two camps here, two possible methods. There's either a dynamic allocation of IP addresses or a static allocation of IP addresses. Now, when we say that IP addresses are dynamically allocated, that means they're automatically assigned. There's some decision being made by a machine or a program to administer IP addresses to every device on a given network. Two examples of this are DHCP and link local. We'll get into those in a second. The other side of that would be static IP addressing, where every device needs to be manually have an IP address manually specified. There are pros and cons to both of these things. Dynamic IP addressing is a lot easier for the human involved in the picture because the machine takes care of all this and takes necessary precautions to not double assign the same IP address to two devices, all that nonsense. But the downside of it might be that you're not really on top of every nook and cranny of your network. You're not responsible for knowing which IP address is assigned to every device, and debugging issues might become a little bit more troublesome. The pros and cons of static IP addressing are exactly what IP address every single device has because you're the one that's administering it. The network can be very tightly managed and controlled, and any outliers or any issues can be tracked down pretty quickly because you know where everything's supposed to be. The downside is it's work. It's a lot of work to manage and a lot of work to maintain.
You kind of got to know what you're doing.
Yeah.
Right? As I mentioned earlier, it's not just randomly assigning a bunch of different numbers. There's the protocols that you have to follow regarding IP addressing to make sure that you've done it correctly, or else you don't have a network.
Yeah, that's a really good point. And oftentimes you won't even have the choice because the environment in which you're networking has already been decided, and you just have to fall in line. But we'll get into the details of both of these things.
And just to be clear, if you're used to working with Shure devices, when you go into our menus and choose what IP addressing you're going to use, we use the words automatic and manual instead of dynamic and static, but they mean the same thing.
That's a good point. You might see those terms and others on different products as well too. It's just, but the core of it, this is what they mean. So in the world of dynamic IP addressing, there's sort of two possible ways that the devices can obtain an IP address. DHCP is the first. It's probably the most common as well. So DHCP stands for Dynamic Host Configuration Protocol, and what it means is that there is an entity, what we would call a DHCP server, present on a network, and its responsibility is to give out IP addresses. It's just that simple. So when a DHCP server is present, every network device that comes onto the network, it takes the responsibility of assigning a unique IP address one by one to every device that needs it.
Assuming that device is set to receive an IP address automatically.
An excellent point. Yeah. So that's the other side of the equation, is that a DHCP server needs to be present, but it's not a dictator. It's sort of a friendly leader. It's not as authoritative as it maybe should be. So when devices come on the network, each network device can be configured to receive an automatic IP address or not. So in order for a DHCP network to happily exist, a DHCP server needs to be present, and all of the devices on that network need to be enabled to receive an automatic IP address. And this is a method that's very commonly used in production. One thing I want to mention is that a DHCP server can come in many shapes and sizes. Typically, a router, or like a wireless router you'd buy at Best Buy, often has DHCP capabilities. That's totally a feature you'd see on the box. And for small networks that are sort of closed and not hooked up to anything else, it's what I would recommend personally. It's the easiest way to get a bunch of gear up and running without having to worry about details. One point I will warn on, though, is that you can't have more than one DHCP server on a network. You can really confuse you're basically got too many cooks in the kitchen at that point, and
It's chaos.
yeah, it's just not it's not a networked practice that is ever acceptable. One last thing I'll say is that any DHCP capable device typically has the ability to turn that DHCP-ness off, that dispatching of automatic IP addresses. You can normally turn that off in the control interface for a router, for instance. So link local is similar but different. So let's say you have a network. You've got devices on that network. All of them are primed to receive IP addresses automatically, but you don't have a DHCP server. This is where link local comes in. This is where all of the devices on that network would, they don't explode, they don't cease to exist. What they do is they go to what is called a fallback IP address. And this fallback IP address it's an IP address in a kind of an arbitrary range, but that's sort of universally accepted as the fallback IP address range. You saw in our example earlier, we had the IP address 169.254.whatever. This is the fallback IP address that's sort of commonly accepted by all network devices. So the device comes on the network. He's primed to receive an automatic IP address, but no one's there to tell him where to go, and he goes back to this IP address. And this IP address is sort of generated randomly based off the MAC address. So as to just like reduce the chance that other devices have the same.
Remember, all MAC addresses are unique to a device, right? So that's why the fallback is randomized off that MAC address, so that you will not. That's how this works. If that wasn't the case, if these things couldn't assign themselves a unique IP address, the whole idea of link local would collapse.
Yeah.
Right?
So what you need to know about link local, two things. One, if you're working with network devices and you see that a device is set to 169.254.something.something, chances are it's in its fallback IP address. And there's nothing wrong with that. You can sort of sandbox devices in your workshop before you deploy them to a professional setting. In the link local fallback IP address range, there's nothing wrong with that. But the thing you do need to know is that if a DHCP server comes online when a device is in that state, it's going to get a new IP address likely and snap out of that subnet into whatever the DHCP server gives. And perhaps the most important thing is that you probably shouldn't use devices with this IP address in production, just because of that susceptibility to being changed. They're basically sitting ducks waiting to be told what to do. It's not a state that you want to use your devices in, especially in a production environment.
Yeah, link local is basically like a backup plan.
Yeah.
But if you're thinking of doing automatic IP addressing, you really should have a router in there. Otherwise, think about static. But again, the troubleshooting tip here, and this is something we tell people all the time, is if you've got a network of devices connected together and you're using DHCP in one device or two devices, they're not on the network, assuming the cable is plugged in, is go in and look at the IP address. If you see an IP address of 169.254.something, that's the fallback, and that means that particular device for some reason is not getting an IP address from the router. So when you see that number, that's your first clue that that thing is not right, or it's one of these things is not like the other, right? And then you should know that needs to be addressed.
I want to clarify real quick. When you say router, what you really mean is DHCP server.
DHCP, sorry,
right?
See, that's old habits die hard.
and the terms often are used interchangeably, so you should be prepared to hear that. But it's the DHCP server that is the thing that gives IP addresses that routers often have and often are used for, but you can have them separately. Yeah. And you can have a switch that has a DHCP server. You can have a router that doesn't have a DHCP server. You just got to be aware of the features and functions.
That's how they tend to get paired together, and that's why I slip and still do that.
No, it's good. For years. You're prepping them for what they're going to hear in the field.
Right. Okay, so that's the ways that, again, you get an IP address. Again, we didn't talk too much about static IP addressing because that was a whole nother webinar all on its own, just to teach people how to do static IP addressing properly. But
suffice it to say that if you are in an environment where devices are statically receiving IP addresses, you either know what you're doing or someone else does. And you got to get in touch with that person just to make sure that you know how many IP, if you want to network your devices on that network, know how many IP addresses you need, ask for them, and make sure that you stick to them. Yep. That's basically it. We have some more tips for what to talk to your IT guy about in the future, but. So moving on to networking your computer. Your computer falls right in line with all of the pro audio gear or any network device that you might be trying to hook up together. We just wanted to call out a few points about, some specific details about connecting your computer to a network, what the notion of network interfaces means, and then maybe how to find your computer's IP address, just in terms of troubleshooting and general knowledge. All right, so I guess the first question is, when you're connecting your computer to a network, what are you connecting to? Are you connecting your computer in your workshop to one device you just bought, or are you at some big center where you're performing some network administration and you're connecting to a whole bunch of devices? They're considerations to take, especially in the latter scenario, particularly whether you're on a standalone or a corporate network. So a single device connection looks like this. If you buy a Shure ULXD receiver or any network device, and in your basement you're just tinkering around, seeing what the thing can do, and you hook it up to your computer, this is what you do. It's a relatively safe environment. You're not going to tear down, your corporate network or your family's Wi-Fi, likely. But just an interesting tie-in with what we talked about earlier is this is a prime example where you'd probably be operating with fallback IP addresses. Typically, computers are not DHCP servers, and typically the network devices you're connecting to aren't either. So in this scenario, when you want to connect your computer to a device, make sure that both the device and, more importantly, your computer, well, both of them, I guess, are important, are in the same fallback IP range. Otherwise, you'll be in different networks, different neighborhoods. The mailman can't get from Phoenix to Boston, and the mail never, well, in this land of mail, then it can't get from A to B, and you'd be out of luck.
And just to bring a physical aspect to this as well, this connection can be done using a standard Ethernet cables. People often ask, if I'm going to do this, do I need what's called a crossover cable, which is a cable where two of the pins on the RJ45 connector are reversed on one side? And that is not needed for this type of. You used to need those like in the older days of Ethernet networking, when you wanted to hook two computers directly to each other without using a switch or a hub. You needed what's called a crossover cable. It's not required. You can take any of our Ethernet products, plug it right into your computer with a standard cable. Assuming both devices are set to automatic, they'll fall back to an IP address and you're done. But it's probably worth pointing out, we'll probably talk about it here too, is that your computer can also be set for dynamic or static IP addressing. So when you do run into issues with getting your computer hooked up to the rest of the network, you're checking the same stuff that you would check on the devices. Make sure it's, if it's supposed to be automatic, make sure it's set for automatic. If it's supposed to be set for static, make sure it's got, a valid subnet and a valid IP address in that same range.
Yeah, I mean, you're literally, as Gino said, the computer has the exact same considerations that the device would. In this scenario where your computer is connected to a network of devices, you just have to be considerate. If you're connecting to a corporate network with a ton of other gear, you probably don't want to bring your own DHCP server and start messing with things. Chances are someone's already managed that. And you want to be cognizant of the type of addressing that's going on. Some corporations use DHCP, where everybody just gets an IP address dynamically as you go. Some networks heavily administer the IP addresses that are assigned to devices. So ask your IT professional, or ask your, the person in charge of your network. One key difference I want to call out is a standalone versus an existing managed or corporate network. What a standalone network means is that if you take you see my crazy spider of devices here with the green switch in between. Imagine that the network that existed here is just as we saw it, where you could draw an entire circle around all of the devices in the network, and there's no other big, like, you control all of the devices in this little closed network. If that's the case, where you own everything, and your network doesn't touch a greater network or the internet or anything like that, I would call that a standalone network. And in those scenarios where you control everything, you can have a little bit more liberty.
You can do the network the way you'd like to, because it's just your own little personal network.
Right. It's when you're interfering or touching somebody else's network that you have to be a little bit more considerate.
Mm-hmm. Okay. There's another point I was going to make, and I blanked out on what it was about that.
Oh, it'll come.
It'll come back later.
So network interfaces. Your computer is unique in that it's got more than, typically, at least contemporary computers, have more than one way to connect to a network. And the two most obvious ways are either through Wi-Fi or through the physical Ethernet cable itself. And this is relevant because when you're networking with devices, I'll use Wireless Workbench, the product that I work on here at Shure, as an example. You're telling an application to look to a network where it can expect to see devices. And corresponding with Gino's comment about being specific, you need to provide specificity to the application about where to look. Now, every application and every device has, every computer might have different needs, but As Gino's pulling up right now, you should be aware of the network interface that your computer uses for certain connections. And so each network interface, as Gino shows in the preferences, so Mac is wonderfully cryptic in naming their network interfaces. But this is a list of all the network interfaces that this Mac has that we're on right now. There are many, and you'll see most of them if you look at the IP address right here. This is the actual IP address that the computer's network interface has. So I'll tell you from experience, I know that EN0 represents the hardwired Ethernet. And you can see a lovely IP address from our corporate network that's been assigned to that network interface. So this breaks the paradigm a little bit of one device, one IP address. But really what you can see are these are just different routes, different avenues, different networks that a computer can connect to.
It's not so much about your computer's IP address as the network interface on your computer's IP address, because you're on your computer, because your computer can have more than one network interface and each one can have a different IP address. And that's why we're seeing a couple of different things here. So yes, this one is the corporate Shure network IP address, which is what's allowing the webinar to go out to you guys so you can hear it. This one here is a secondary. I have a USB to Ethernet adapter that's connected to the SMA20 automatic mixer that is running on a different network with here's the quiz part. What kind of address is this? A fallback IP address. And you know that because it's 169.254. So there is no DHCP server because the SMA20 is connected directly to my computer. But if that happened to be where my wireless receivers that I was going to use with Workbench were connected, I would go and click, oh, I need to click here so that the software that I'm using, in this case, Wireless Workbench, knows which Ethernet adapter I'm on my computer to look for.
Yeah, the takeaway here is know that your computer has access to more than one network. And in an instance where your computer is reaching outside of itself to talk to other devices or other entities on a different network, make sure you're using the right interface, you know?
So how do you know what your IP address your computer actually has?
Oh, that's a great question, Gino. You know, it might seem like it's not relevant, but it's extremely relevant when when you network your computer to other devices. Don't think of your computer as anything special. It's just another one of the network devices that has to follow all the same rules that those devices talk to. You can find the IP address of your computer in a few ways. There are ways in the operating system that are convenient and GUI-ful, like control panel on Windows, system preferences on Mac. But you guys are hardcore audio guys, so I figured we'd talk a little bit about the command line way to do it. It's a little bit uglier, but it's always right, and it's a lot less subject to change with the tides of operating system updates. So there's a really simple command line string that you can type in to get all the networked information about your computer. On Mac, it's ifconfig. On Windows, ipconfig, but I'll show you in detail what each output looks like per platform. So on a Mac, if you open the terminal application and type in the string ifconfig, one word, and hit enter, you're going to get a big vomit out of text. That's what this is right here. And what each one of these line items shows you is one of the network interfaces that we just mentioned. A lot of this information probably isn't relevant. I circled in green the stuff that I think is. The first one I circled in green is the interface name. This is the cryptic code on Mac. On Windows, they do a better job of labeling them. The second thing is the actual IP address of your computer. And again, don't be too bogged down in the details here. This is merely a tool to help you see the raw information corresponding to the network connection your computer may have. But if someone were to ask you what's your IP address your computer's occupying, this would be a great way to show it. In Windows land, if you the way I know how to get to it is run to the command prompt in the start menu, go to run and then type CMD and hit enter. But I'm sure you guys know a better way to get there. Then you type ipconfig, not ifconfig, and hit enter. This is the blurb you get spit out, and it's actually a little bit more intelligible. The network interfaces are subdivided as well, but they have labels that are meaningful. The top one is labeled Ethernet adapter, local area connection, which corresponds to a physical connection from an Ethernet jack. And what I've circled shown is the IP address and the subnet mask of this Windows machine. So just a little fun, technical, nerdy thing for you to try at home if that's ever relevant. There are other ways to do it too, but a quick Google will certainly expose other ways to get the IP address of your computer.
So the last thing we want to talk about here, just kind of quickly before we take some questions, is the concept of networked audio as well. And again, this is just kind of a quick look so we can talk about some of the considerations that apply to the overall topic we're dealing with here. But if you are interested in learning more There's actually, we've done a whole previous webinar on this topic that's archived at shure.com/training called How Shure Products Connect Using Dante, which is a specific network audio protocol that we've adopted here at Shure. There are others. That's the one that we've kind of thrown our lot in with. Again, digital audio, what makes digital audio networking different from digital audio transport is digital audio transport is taking your digital audio signal and just moving it from one place to another, like using the optical digital output of your Blu-ray player to connect it to your home theater system. That's kind of a one-way, single connection. But in digital audio networking, what that means is that you're basically taking the audio output from your device, the digital audio output from your device, and putting it on a network so that other devices can easily get to that audio. So rather than just a one-to-one connection, it sets up a network of devices that can all utilize and route that audio. So in the interest of time, we'll skip right to different audio networking protocols that exist. There's things like MADI, AES-10 specification that kind of exist in their own little world. And then there's the audio over Ethernet type of digital audio networks that there are many different types out, and they operate at what called different layers, and that's another networking topic, Ethernet topic, that we didn't really even get into, is the concept of the layers. But suffice it to say, some of them just exist at what's called the physical layer, or layer one, which means that it's audio over Ethernet only in that it uses standard Ethernet hardware, that is Cat5e or Cat6 cable and Ethernet switches, but the actual communication doesn't follow any Ethernet protocols. So things like Avion's ANET, the AES-50 standard, these are physical audio over Ethernet type connections. But when you get into layer 2, now you're looking at things like Ethernet and Cobra Sound that are actually using Ethernet protocols for the communication. And when you get into layer 3, things like Dante and QLAN, kind of the advantages there, particularly one when we talk about Dante, is that they can even coexist on data networks there, whereas something like CobraNet kind of has to exist as its own little network. Some of these newer technologies, your digital audio goes on the same network as can go on the same network, I should say, as your corporate email system does, or whatever. So there's no reason that the digital audio can't be shared with everything else that's kind of happening on your network there. So that's sort of how these kind of systems have evolved from a very standalone sort of thing that just uses the physical hardware of an Ethernet network to something that essentially is an Ethernet network. And again, the advantage is, you may probably seen this before. It's sort of obvious, right? Instead of having a dedicated one-to-one path for every single analog mic channel you want to route between your receivers and your mixer, if you've got like a Dante enabled receiver here, it's just a matter of taking the digital audio output, which is on the network card of your device, hooking it up to an Ethernet switch, which of course your Dante enabled mixer in this case is also plugged into that same Ethernet switch. And then all of your connections, all of your audio patching is done in software. You just have to get these devices on the network. Physically, it doesn't matter which port on the switch they're plugged into. It doesn't matter physically where in the building they're located. Once they're on the network, they become available for routing purposes. And that routing is actually done. I'm just going to skip ahead here in the Dante controller software for using a Dante enabled device, right? So the little checkboxes represent an audio path that's been made between a mic channel to a mic output to a channel on a mixer, or from a mixer output to an amplifier, or whatever it happens to be. It's all done in software. And again, some of the advantages to the Dante, which is what we've gone with. You've got over 1,000 channels of bidirectional uncompressed digital audio available over Ethernet using off-the-shelf cheap Cat5e, Cat6 cable. Much easier than dealing with large, heavy snakes and all of the problems that come with long audio cable runs, hum, buzz, and that sort of thing, right? So it's all just digital audio packets running around your network, right? And again, Dante is great because it works on shared networks. It doesn't have to be isolated off by itself, and it's extremely low latencycy see. You can see the laundry list of other companies that have jumped on with Dante. The list keeps growing and getting bigger with each time. I was happy to even be able to add Biamp to the list of companies that now support Dante. So it's getting to be quite the thing. Again, there are other protocols. That's the one that we happen to use. Some specific considerations when you're doing network digital audio, one of which, particularly with Dante, is gigabit switches are recommended. Again, you really want to be able to handle that kind of traffic on a network. and manage what's called a managed switch is typically also recommended. And that's a switch that has some sort of DSP or a GUI on it that allows you to configure the switch. A lot of times they have something called quality of service, which again just improves the performance of the overall digital audio network. You should be avoiding green Ethernet switches, green as in, environmentally friendly. I know it's probably not a good thing to be encouraging right now. But in the case of digital audio, you don't want to be using a switch that might look at a given Ethernet port on your switch and say, that one's not being used right now. I'm going to turn that off. Yeah, that's probably not a good idea for live audio purposes. So you probably want to watch out for those in an audio application. Shielded cable, shielded connectors are always recommended. And also remember that in the case of like Dante devices, there could be multiple IP addresses per device, because there's an IP address that's associated with the control aspects of the device for, say, manipulating a ULXD receiver and wireless workbench. There's a separate IP address for the Dante aspect of it. So you might actually need more than one IP address per device. In fact, that's shown on the Microflex wireless utility page here, where you can see the IP addresses for all of your Microflex wireless devices. You'll notice there's an IP address for control in this column, and then for networked audio on the access points in this column. And those are two different IP addresses. So this is important when you're going on a corporate network and you're getting IP addresses from the corporate IT department. You need to specify exactly how many IP addresses you need, and in some cases, per device, you need more than one. So to kind of brings us to this, I guess, good way to kind of end things and summarize things here is, communicating with the IT department. What are the things that they need to know when you're going to be integrating stuff on a corporate network? And of course, how many devices? And second to that, how many IP addresses? Because there could be, you need more IP addresses than physical devices. But all of those things need to be made aware to the department. You need to make sure that they know that all these devices, if they need to interact with each other, typically need to be on the same subnet. That's definitely true of all Shure network devices. If you want them to connect to each other and connect to the software, that means the computer also needs to be on the same subnet as all those devices. They don't cross. Find out what kind of IP addressing the IT department is using, static or automatic, so that you can set up your devices properly. There may be some concern about how much traffic these things are going to throw on the network. Using MXW as an example again, if it's just data only, it's less than 0.02% of a gigabit network. Even if you're doing Dante with something like, I think we tested with like 120 channels of Microflex wireless running on a network with Dante, it's approximately 1.28% of a gigabit network. So very low traffic, and not something that they really need to be worried about. If the IT department needs to do VLANs, which of course is a topic we might cover in part 2, just be aware that yes, our devices can support VLANs as long as everything's on the same subnet. And there is some level of security for the data and control aspects of it that's password protected on our GUI-based products. Dante is not encrypted and there is no password, but we can provide more information on Dante, how to deal with that if necessary. And finally, coming back to the ports and protocols topic again, I don't want to dwell on this because we're already out of time and haven't taken any questions yet. We'll hang out for a few minutes though and take some questions. But just be aware again, like I said earlier, that there's certain ports on a network that need to be open for these devices to work. These are ports that need to be open for Shure's MXW devices and SCMA20 automatic mixers. So if you're trying to do some of these things and the IT department has shut down some of these ports or nailed shut some of those windows, then you might have some issues. So that's after all your IP addressing and everything else is sorted out, something to look at with the IT department would be like, are these ports open? And you can get this information from the manufacturers. So that was a lot of stuff. I'm just going to turn it over to Cheryl and see if there's a few questions we might be able to answer before we call it a day here.
Okay, we do have just a few quick questions here. On the subject of cables, do shielded RJ45 connectors ever get used on non-shielded cable?
Shielded connectors on non-shielded cable. I suppose you could do that, but you would be missing the advantage of the shielded cable and shielded connector.
Okay. Can networked audio exist on a company's network without degrading performance of the data network or the audio network?
Yeah, yes, I think that question maybe was asked before we got to that part of the subject, but yes, I should say that's not true of all. Again, something like a Cobra net needs to exist on its own. It's its own network. It just happens to be using stuff that looks like it could be part of a corporate network. But things like Dante exist perfectly well on a corporate network with very, very low interference to what else might be going on in the network.
Okay. What is the latency with Dante?
The latency in Dante actually, I don't want to use variable. It's user selectable. It can be, in other words, um, Dante guarantees a specific latency that the user can choose, and then the system adjusts itself to always maintain that latency throughout it. And there's different variables. I think for most small networks, it's around a millisecond or so. But for larger networks with more devices, you might have to set a higher latency to be able to deal with the larger number of devices.
And I think one thing I want to add to that, I think Gino, you could probably clarify this a little bit more, but it's not like you can choose a latency of 0 and just like,
Well, that's true. Yes,
because
it can't be 0. There has to be some latency.
you choose a latency, and then that which cannot be delivered in that speed is just dropped. Am I correct?
Exactly.
So you basically want to deal with you choose as much latency as you can deal with, such that none of your channels are dropped.
Exactly.
But there's a give and take that you can control.
Yep.
Okay. What are some of the other protocols besides Dante, and what are the pros and cons of those others?
Okay, well, that's probably a whole nother webinar in and of itself. In fact, you should probably go back and watch the webinar on Dante, because that was done with my friend Landon Gentry over at Audinate, who makes Dante, who kind of goes through some of those things in more detail. But again, not to keep picking on CobraNet and EtherSound, but those are older protocols that were revolutionary and groundbreaking for their time. But kind of the main advantages of those is much longer disadvantages to those is much longer latency, and the fact that they had to be on their own separate network versus Dante. Another protocol you might hear about, which is not really a protocol in and of itself, but it's a set of standards, is what's called AVB. That's probably the primary one that people get asked about as a comparison to Dante. The difference is that Dante is a product, for lack of a better term, made by a company called Audinate, and manufacturers like Shure and Yamaha and others buy the ability to use Dante from Audinate. AVB is essentially an open standard, right? It's being put together by a working group called the Avenue Alliance to an IEEE standard for digital audio networking. The disadvantage, I guess, to AVB is that it doesn't really exist yet. There are a few products out there that are using AVB, but the standard hasn't really been fully implemented yet, and there's not a lot of products out there that are using it. And also, AVB requires specific AVB switches. You have to buy an AVB authorized switch, of which there's not a whole lot out there yet, to be using AVB. Whereas Dante uses any standard Ethernet switch. As long as it's gigabit, we don't really care too much about what it is. So that's kind of a quick high level view of some of the things, but it's a big topic.
Okay. Great. Well, I think that just about wraps up the time we have. I think there are a couple questions that we didn't get to. So if you didn't get your question answered, or you have another one that pops in your head, please feel free to send us an email at support@shure.com, and one of our applications engineers will be happy to answer any other questions you have. There were some comments and questions about this being available for future viewing. And as I mentioned at the top of the webinar, it is recorded and will be archived in our archives at shure.com/training, probably early to mid next week. So you can always go there, find all of our past webinars and this one as well as information, I believe, about upcoming webinars. So that about wraps it up for today. We hope you all learned something, and we will see you next time.